ever been stuck in a remediation project that ended up costing way more than you budgeted? Or perhaps you were left with unused funds because you overestimated the cost? It is a common struggle. The uncertainty in soil remediation's costs can turn a promising project into a financial nightmare. But what if there was a way to minimize the uncertainty? A method that can give you control and confidence in your budgeting? Welcome to the world of Conditional Gaussian Simulation, a cutting-edge approach that can help you assess the uncertainty of your contaminated soils remediation projects. Whether you're a seasoned expert or just curious about the field, our course is designed to guide you through this revolutionary technique. Join us and turn uncertainty into an opportunity. Discover how to take charge of your projects and make informed decisions that can save time and money. Ready to change the way you investigate and evaluate the contaminated soil remediation? Hello and welcome back to the Conditional Gaussian Simulation course for environmental modeling. My name is Marcel and I'm the main instructor of this course. This is the lesson 6th, and today we are going to be evaluating the remediation cost for a contaminated site using the Conditional Gaussian Simulation technique. Let's start with the workflow diagram with the main points that we are going to see in today's lesson. This is a Geo-statistical lessons offered by the Geo RGB community at gscourse.online. The title for this lesson is the Conditional Gaussian Simulation for Uncertainty Assessment of Soil Remediation Cost, and this is a step-by-step workflow guide. The first point for today's lesson is going to be the data and libraries loading. In this project, the majority of the time we are going to be working with the software R, integrated with the R Studio. But we are going to be using also QGIS a little bit for quality control. The first thing that we are going to do is to load all the libraries that we are going to need for executing the scripts that we are going to be creating. We are going to be working with the Meuse River dataset, a very famous and free database related to contaminated soils. And in this case, we are going to work with the zinc parameter. As I believe you already know, this dataset has the X and Y coordinates, has several heavy metals and also other parameters. But in this case, we are going to be working with the zinc concentration. This concentration is in ppm. The next thing that we are going to do is the exploratory data analysis. In this case, we are going to compute the histogram for the zinc concentration, and we are going to see the basic statistics associated with this data. Later, we are going to transform our original data set, that is the zinc concentration in ppm, in a data set that follows a perfect normal distribution using the technique Gaussian anamorphosis. Then the first thing that we have to do is define the anamorphosis model. And later, when we define this model, we can make the transformation in order to have a new data set that is following a perfect normal distribution, as you can see here in this graph. Also with a mean of 0, median of 0, a standard deviation of 1, and a very symmetric histogram where we have, in this case, the minimum value is minus 2.8 and the maximum value is 2.76. Then you can compare this histogram that is showing a perfect Gaussian distribution with the original dataset, where we have a very skewness histogram. Remember that it is essential to have a data that is following a Gaussian distribution if we want to work with the conditional Gaussian simulations. Then to make this kind of transformation is something mandatory. We are not going to spend too much time with these 3 points: the data and libraries loading, the exploratory data analysis, and the Gaussian transformation with the Gaussian anamorphosis, because all these 3 points were already explained in the first lesson of the Conditional Gaussian Simulation course, where we explain, extensively the Gaussian anamorphosis method. Then my recommendation is just to watch this lesson, because here in this lesson we are going to pass these 3 points very fast. Then the next thing that we are going to work on is going to be on the variography analysis. This analysis is going to be completed on the transformed data. Then the first thing that we're going to do is to create the experimental semi-variogram, and later we are going to fit a model on this semi-variogram. We need to know what is the structure of our data set in order to know the Nager effect, the partial seal, and the range of our data, because we want to replicate this information on the conditional Gaussian simulation. The next thing is going to be the estimation and simulations. To complete this task, we need to load the interpolation simulation grid. For the estimation, what we are going to do is apply simple kriging. In simple kriging, we are going to create the prediction map and also the variance map. Remember that the variance map is related with the error. And for the simulations, what we are going to do is create 100 simulations. And here we have just one example related with the simulation number 12. I decided to do 100 simulations in order to have robust statistics for our final results. But as you are going to see, 100 simulations is not that much. You are going to see that when we execute the 100 simulations, it doesn't take very long time. Computationally speaking, it's not really big according to this data set. Then I decided to take 100, but also 1000, it's not going to be an exaggerated number. As bigger is the number of simulations, more robust are going to be the statistics that you get from that simulations, and at the end, better are going to be the results, more realistic. In this case, the visualization of the maps is created with the package simple feature, but also we are going to use the other packages to visualize the maps. For example, it's going to be the raster package. Then the next thing that we are going to do is to the back transformation. Remember that here the results that we have is with the parameter zinc concentration that we transform using the Gaussian anamorphosis. But at the end, what we want is to have the maps in the original scale. The original scale is in par per millions. Then in this point, what we're going to do is to reverse the data to the original scale. In this case, par per millions for the zinc concentration. The next point is going to be exporting all the maps to QGIS. In this case, we are going to have the maps that we created with the Gaussian anamorphosis values and the maps that we back transform. That is going to be the maps with the concentration in part per millions. Then we are going to open all these maps in QGIS. Here we have the examples. We have the simple kriging maps for the prediction and also for the variance with the Gaussian anamorphosis values. And here we have the conditional Gaussian simulation. It's just one map for the Gaussian anamorphosis. Then we have the same maps, but in this case with the back transformation for the simple kriging and for the conditional Gaussian simulation. Here I put just an example, the simulation number 10, but you have to be aware that we have 100 simulations. I believe it's really important to know how to export the maps from R to QGIS, because in QGIS we can make a very nice edition for the maps. If we want to publish any map, the options that we have to edit that map in QGIS is so big compared with the possibilities that we have with R. In R, the edition of the maps, it's pretty complicated, and the results are not as good as you can get in QGIS. Again, in this lesson, we are not going to spend too much time in the points 4, 5, 6, and 7, because most of the information that we are going to see here was already explained at the previous lessons. In the lesson 2, we was talking about the simple kriging. Then all this section it was covering in this lesson. Also, we was talking about the limitations of the kriging model. And in the lesson 4, we was introducing the conditional Gaussian simulation using QGIS. Then also this section was explained over here, and the back transformation. Then my recommendation is, if you want to have a very extensive explanation about all this process, you can watch these lessons over here. Then what is the difference between these lessons over here and this lesson over here? Well, today we are going to be using just R. Then we are going to write all the code in R, and we are going to run the scripts, right? But here, what we was doing is creating the R scripts to be integrated in QGIS. In that way, what we get is an interface. Then we can use that QGIS interface to load the data and then run the scripts and get the results directly on QGIS. Then here, we don't need to export the information to QGIS because we are already using QGIS. But in this case, we was using R, and then we have to export the maps to QGIS. Then the main advantage of using an R script integrated in QGIS is that we don't need to create every time that we are working with a different project a new R code. We can use that interface that we created, and then when we have the script created, we can use that interface for different projects. But when we are using R, we have to write the code every time, right? That's the main difference. But the advantage of using R is that we can run a lot of simulations, that in this case we run 100 simulations. And when we was doing the integration of R scripts in QGIS to do the conditional Gaussian simulation, we did for 10 simulations. When we want to work with a big data that implies to create a lot of simulations, to use R Studio with R, it's more efficient than using QGIS. Then that's the limitations that we have with QGIS, right? That we cannot run a big data sets because the process is going to be complicated, slow, and in that case, it's better to use just R, right? And that's the main difference between these two. But again, the advantage is that when you have the integrated R script in QGIS, you can use that interface for any project, right? And if you want to run just a very few simulations, you can use QGIS, and it's going to be very efficient, and you are working just with one environment because you are working just with QGIS because the script is already integrated. And then you don't have to be worried about exporting the information from R to QGIS. Then with these lessons, you're going to have the R scripts integrated in QGIS, and with the today's lesson, what you are going to have is just the R scripts. But if you take these ones and these ones, then you can decide if you want to use just QGIS or if you want to use just R, depending on the necessities of your project. But you are going to have the both options. The next point is going to be the number 8, where we are going to evaluate the contamination. Let me make some zoom over here. To do that one, we are going to take each simulation and we are going to reclassify the pixels. What we are going to do is to create 4 levels of contamination. It's going to be the low level, the medium level, the high level, and the very high level. And here we have an example for the low level of contamination. Then we take the simulation number 7 and we reclassify the pixels with just two values, 1 and 0. When the pixel has a value of 1, it means that the range of the concentration in that pixel goes from 251 ppm to 500 ppm. But for the rest of the pixels, that in this case doesn't have any color, the concentration is going to be lower than 251 or higher than 500. And we are going to do this reclassification for all the simulations, for the 100 simulations, for all the levels of contamination. And for example, for the low level of contamination, the range is going to be from 251 to 500. For the medium, is going to be for 501 to 750. For the high, is going to be from 751 to 1000. And for the very high, is going to be any pixel that has a concentration bigger than 1001 ppm. And the question is, why you take for the low level this range? Because I was using the Alberta Tier 1 soil remediations guideline. Every country, every province, they are going to have their own guidelines. And in this case, for soils that are using for agricultural, that is the ones I'm thinking we can use for the Meuse River dataset, the limit of the concentration, the guideline is 250. Then any value under 250 is considered that the soil is not contaminated. But any value of zinc that has a concentration bigger than 250 ppm is going to be considered as a soil contaminated. For the agricultural area, if you are working in a commercial area or industrial area, the guideline is a little bit different. And also the guideline sometimes depend on the granulometry. If you have fine soils or if you have coarse soils. But in this case, for both type of soils, we have the same guideline. We already discussed this topic at the lesson number 5 of the Conditional Gaussian Simulation course. It was this lesson where we was evaluating the uncertainty of contaminated soils. In this case, what we did is to create R scripts to be integrated in QGIS to reclassify the pixels in an automatic way. However, today what we are doing is learning how to do this process using R, only R, and also we are going to see how we can make a quality control with QGIS using both softwares. You know, calculating the classification of the soils using R and also calculating the classifications of the soil using QGIS. Then we can compare the results and we need to have the same results. And if we have the same results, we can say that we pass the quality control for the classification of the soils according to a specific range of concentration. However, in this lesson, what we are not going to do is to create a reclassification map for each simulation for each level of contamination. That is too much work. We don't need to do that one. We are just creating one map for the simulation number 7 for one level of contamination as an example. Then with this example, if you need to create any other map related with one simulation with a specific level of contamination, you already know how to do it. But we are not going to do that one. We just did one as an example. What we are going to do is to create a data frame for each level of contamination, where we are going to have the number of the simulation, like you can see over here, with the total number of pixels in that range of contamination. Then here we have the example for the low level of contamination. Then we are going to have here a column with the number of the simulation. In total is 100 simulations. And next to the number, what we are going to have is the number of pixels in that range of contamination, in this case the low contamination, the number of pixels we have in that range. For example, in this case we was working with the simulation number 7, and in the simulation number 7 for the low level of contamination, what we have, as you can see over here, simulation number 7, number of pixels is 661. Then we're going to have one data frame like this one for each level of contamination. Then with these data frames, what we are going to create is a histograms. Then we are going to create 4 different histograms, one for each level of contamination. Here we have for the low level that is ranging from 251 to 500 ppm. Here we have the histogram for the medium level that is ranging from 501 ppm to 750 ppm. Here we have for the high level of contamination ranging from 751 to 1000, and here we have for the very high level, that is the pixels that show a concentration higher than 1001 ppm. Now let's go to analyze what kind of information we can see in this histogram. This histogram, remember, that is for the low level of contamination, and we created this histogram with the data frame corresponding to the low level of contamination, where we have the number of the simulation and the total number of pixels with that range of concentration. At the x-axis, what we have is the number of pixels, 500, 600, 700. And at the y-axis, what we have is the number of simulations. Then, for example, this bin over here has more than 25 simulations. Here we have 20, 25 is going to be around 27, 28 simulations for this bin. And this bin has the number of pixels ranging from here to here. Then if we make some zoom, we're going to see that here we have the value of 600, and this one is 650. Then the bin is ranging from, for example, 590 to 620. That's the range for this bin. Also, as you can see on the top, as a subtitle, we have the statistics associated with this histogram. In this histogram, we have 100 samples. That is the 100 simulations. Each simulation is like one sample. Then we have the mean value, we have the median, the standard deviation, the variance, the minimum number of pixels in the 100 simulations, and the maximum number of pixels in the 100 simulations. It means, for example, that here we have just one simulation. This one also is just one simulation. And this simulation, that I don't know what is the number of this simulation, we have the minimum value. And the minimum value is 511 pixels in that simulation that range from 251 to 500. And here we have one simulation that is showing the maximum number of pixels in that simulation, that is 760 pixels, ranging with these values over here. Then, as the histogram is showing a normal distribution, a bell shape, and also the median and the mean value, they are very close to each other, we can say that this histogram is very robust, right? And the mean value is a very good representative of all the data set, of all this data set, all this data set over here. Then as the histogram is robust, and we can say that the mean value is representative of all the data set, we can say that the mean value is the most probable scenario. Then if you are taking, for example, one random simulation from those 100 simulations, the highest probability is to have this value, the 619 pixels with that concentration in the simulation. It doesn't mean that you cannot get this value. You can get this value, and you can get also this value. This value is the best scenario because it's the smaller number of pixels in one simulation with this concentration. And this scenario is the worst scenario because it's the highest number of pixels with that concentration. And as you know already, one pixel represents 40 by 40 meters. And 40 by 40 is a surface of 1,600 square meters. Then, if you have this simulation, it means that the extension of the contamination in this simulation is bigger than the extension of the contamination in this simulation for this range of concentration. Then at the end, the simulations give us a range from the minimum value or from the minimum extension of contamination to the higher extension of contamination. And also we can get the average, the mean value that is the most probable X scenario. This X scenario can happen, but the probability is very low because it's just one simulation in 100 simulation. However, the bins situated here at the middle, it represents more than 80% of the total of simulations. Then all these bins at the middle of the histogram has more chances to be the real X scenario because they have higher probability. Again, with this X scenario also can happen, but the probability is very low. And we did this study for 100 simulations. Can you imagine, for example, if we are doing for 1,000? Then the mean value is going to be even more robust, more representative of all the data set. If we have the conditions of a perfect normal distribution, and also if the mean value and the median value, they are together, right? That's the way that the mean value is going to be representative of the data set. And then we did, for each level of contamination, these histograms, and then we get the values associated with the data set. Then you can see that all these histograms, they are showing a normal distribution, and the mean value and the median value, they are together. It means that the mean value is representative of the data set. Then we can say, for example, that for the medium level of contamination, ranging from 501 to 750, the highest probability is to get a simulation where the number of pixels in that range of contamination is going to be 452. Then for each level of contamination, we are going to have the minimum, the maximum value, and the most probable situation. Then with all these histograms, what we are going to do is to compile all the information and create one table. And that is going to be the point number 9, where we are going to see the statistics summary and the result analysis. Then here we have the table created with R, where we have the different levels of contamination with all the statistics. And then we are going to export this table as a CSV file. Then we can open this information, that is this table over here, from here to here, with Excel, OpenOffice, with any spreadsheet, just to process the information. And that's what we are going to see in this table here. Now we can use the data that we have in this table to create new information. Then, as we know that each pixel has a dimension of 40 by 40 meters, we know one pixel represents a surface of 1,600 square meters. Then we can multiply the number of pixels by the surface of one pixel. And then we are going to have the total extension. If we are taking as example the low level of contamination, we can multiply the 1600 by the minimum number of pixels, the maximum number of pixels, and also the average. Then we're going to have the minimum extension of the contamination for the low level, the maximum extension for the contamination for the low level, and also the average. Then if we know what is the minimum extension and the maximum extension of the contamination, we can make a prediction related to the cost, right? If we are assuming, for example, that the cost of the remediation for the low level of contamination for 1 square meter cost 1 unit, here I'm not talking about what type of remediation we are going to use. We can use a lot of different type of remediation. We can use phytoremediation, we can use bioremediation, we can use washing soils, we can use excavation. I'm not talking about that one. I'm talking about what is going to be the cost of the remediation for 1 meter square. And you are going to decide what is that cost, depending the method that you are using. But one thing is going to be clear, as bigger is the concentration of the contaminant, higher is going to be the price of the remediation. And in this case, I assume, for example, that to remediate the low level of contamination is going to have a cost of 1 for 1 meter square. Then when I multiply the cost by the extension, I'm going to have what is going to be the cost for the minimum extension, and that one is going to be the cost for the minimum extension. I'm going to have also the cost for the maximum extension, and also I'm going to have the average. And remember that the average is the most probable situation. Then when we are doing this one, now we know that we are not going to have a contamination extension that is going to be smaller than this one. This one is the smallest one, because in 100 simulations, we get this value as the smaller one. And we know that the extension of the contamination for the low level of contamination is not going to be higher than this value, because this value is already the highest one that we get in our simulation. Then, as we know what is the minimum extension of the contamination and the maximum extension of the contamination, we are not going never to under-evaluate or over-evaluate the extension of the contamination. And as we are not going to do that one, we are not going to underestimate or overestimate the price of the remediation. And also we are going to have the most probable situation. But we know that we are moving, the cost of the remediation is moving from this range: minimum cost, maximum cost, and for each level of contamination. Then if we make the summation of all these values, we are going to have the total range to remediate all levels of the contamination. And the total range in this case goes from this value as a minimum cost to this value to the maximum cost. As the average is this value. This value is going to be the most probable scenario. If you want to have full access to the lesson and see how we executed the exercise, to see all the R scripts that we was using, how to build the graphs, how to analyze all the data, just go to the Geo RGB community at gscourse.online, select the Conditional Gaussian Simulation course for environmental projects, and when you get enrolled, you can press the button Start Learning. Then here you are going to have all the lessons related to this course. Then here we have the lesson 0, that is the introduction, the lesson 1, that is about Gaussian anamorphosis, almost 1 hour of content, the lesson 2, that is about simple kriging, 1 hour and a half of content, the lesson 3, that is about the kriging interpolation model analysis, where we saw what is the disadvantage of using simple kriging and ordinary kriging. This lesson is 30 minutes of content. The lesson 4 is implementing conditional Gaussian simulation to QGIS, and also we are going to be analyzing the conditional Gaussian simulation model, comparing with the results that we get with simple kriging or ordinary kriging. In the lesson 5, what we have is the evaluation of the uncertainty of contaminated soils using QGIS. This one is 40 minutes of content, and the lesson for today, that is the evaluation of the cost remediation for a contaminated site. As you can see, this lesson has 2 hours 30 minutes of content. Also, you can follow us in YouTube. Here you have all the lessons. Then it means that you can follow the course, but you are going to see that when you are watching the videos through YouTube, there are some restrictions. I would like to mention also that here at the bottom on the website, you have a tab, exercise files, where you can download all the scripts and all the information that we are using during the lesson. Then you can replicate the exercise. Well, that's it for today. Thank you very much for watching this video and see you on the next lesson.